Which stars are the rarest? Why are they practically missing from the universe? And what makes them so unusual? Obviously, we haven't done a full-on head count of every single star in the universe. We can study the stellar population in our own galaxy pretty well. Plus, we can gather some data on individual stars in a few nearby galaxies. But the truth is, we don't really need to know every last star to figure out that some types occur more often, and others way less often. Way less often. Physical laws are the same everywhere. Sure, different galaxies can vary, but overall, the processes of star formation and evolution are likely similar, say in our galaxy and in some other galaxy 1 billion light-years away. If we start with something basic, the rarity of a star depends on its mass, though that's not exactly our focus today. As I've mentioned more than once, the most common stars in our galaxy are low-mass red dwarfs, or M-type stars. They make up about 70 to 80% of all the stars in the galaxy. The rarest stars by spectral classification are the massive blue O-type stars. They account for mere thousandths of a percent of all stars. So that means at best, there are maybe a few tens of thousands of them in our galaxy, and that's out of hundreds of billions of stars. Interestingly, when we look at the night sky with the naked eye, we see a very, let's call it non-representative, snapshot of the galaxy's true stellar population. With the naked eye, we see exactly 0 of the stars that make up as much as 80% of our galaxy, the red dwarfs. Yet we do see massive blue stars that are actually incredibly rare. Take Orion's belt, which everyone's seen, made up of stars like Alnitak, Alnilam, and Mintaka. Most stars are super dim, while rare stars, on the contrary, tend to be really bright. But today I want to consider not just main sequence stars, but also the different stages of stellar evolution. We observe a star at a particular point in time, but over its lifetime, it can change dramatically. Another factor is the configuration of its system. For instance, if it's in a binary system with a companion, that can create certain rare conditions, and sometimes a specific stroke of luck can result in extremely rare objects. There are objects we only know 1 or 2 examples of in the entire galaxy. Among rare stars and stellar objects, there are types we talk about a lot. Take magnetars, for example, a rare variety of neutron star with an especially powerful magnetic field. Even though we mention them pretty often, only about 3 dozen are currently known. But today I'm going to chat about stars that are a bit less stellar, so to speak, or, well, less popular. Maybe it'll be your first time hearing about some of them. One important clarification, though. We're talking only about objects that have been observed to exist, not hypothetical ones that might exist, but haven't been detected yet. So which stars rank among the rarest? Why so few of them? And what unusual properties do they have? We'll talk about all that and more today. All stars start life in more or less the same way. Initially, it's just an enormous, shapeless clump of low-density gas. But at some point, that clump becomes unstable and starts to collapse. From there, the story can diverge. Maybe it ends up as a red dwarf that lives for hundreds of billions of years, or a giant star that dies off in just a couple million. Maybe it'll be all by itself or end up part of some multiple star system. One extremely rare twist in all this is that your clump of gas winds up as a white dwarf pulsar. You heard me right, a white dwarf pulsar. These might be among the rarest objects out there, if not the rarest. So far, only 2 have been discovered. These objects are super intriguing, but what makes them so weird? We're used to thinking of pulsars as neutron stars. Until recently, it was fair to say all pulsars are neutron stars, though not all neutron stars are pulsars. Now we have to tack on a caveat. There are 2 white dwarf pulsars as well. Just a quick reminder, the word pulsar is short for pulsating radio source, a repeating radio signal. Radio because the first pulsars were discovered in the radio range. Radio signals that repeated with strict periodicity looked unbelievably odd, and at first people even considered the possibility they were transmissions from an alien civilization. You might recall that the very first such signal was briefly labeled LGM-1, Little Green Men. But eventually scientists realized it wasn't extraterrestrials. It was neutron stars with powerful magnetic fields, creating narrowly focused streams of particles. We see them as pulsars on Earth if they're angled so that, as they spin, Those beams periodically sweep past us. If you want the full story of how pulsars were discovered, I covered that in a separate episode about 5 years back. Nowadays, we know not just radio pulsars, though that sounds pretty redundant since radio is already baked into the word pulsar, but also pulsars visible in optical light, in X-rays, in gamma rays, and so on. But for the longest time, pulsars seemed to be the exclusive domain of neutron stars, until researchers began suspecting that something similar could happen to other kinds of objects with powerful magnetic fields. Their main candidate, white dwarfs, and after decades of theorizing, the first one was finally confirmed in 2016. That object is called AR Scorpii, or ARSCO for short. Actually, it was discovered way back in the early 1970s. It's located in the constellation Scorpius. It's extremely faint. You won't see it with the naked eye. Here's the patch of sky where it's located, and here's the star itself. It's a variable star, meaning its brightness changes over time. Its brightness in the visible range goes up and down with a period of about 3.56 hours. For a long time, it was classified as a delta Scuti variable. Those are stars whose overall brightness varies because their surface is physically pulsating. So for decades, astronomers assumed AR Sco was a single variable star with a pulsating surface. And that's why its observed brightness rose and fell. But guess who helped expose the object's true nature? Amateur astronomers. A group of amateurs in Europe was observing variable stars and noticed that AR Sco's behavior didn't match what you'd expect from that type of variable. Their new observations, more detailed than ever, showed the old classification was wrong. They brought in professional astronomers who got intrigued by this oddball and used several major observatories, including the VLT itself, to do follow-up observations. They ended up collecting higher quality spectra and brightness curves across a range of wavelengths. First off, they found that ARSCO isn't a single star at all. It's a binary. You can't always figure that out just by looking, i.e., visually spotting two distinct stars, because if the resolution isn't high enough, both components blur into one. It might still appear as a variable star if the two objects are orbiting their common center of mass. AR Sco turned out to be a tight binary system, even though it's relatively close by cosmic standards, 380 light-years. The stars are only about 1.4 million kilometers apart, which is more than 100 times less than the distance between Earth and the Sun, and just 3.5 times the distance between Earth and the Moon. That 3.56-hour period is the orbital period of the system. The system has a red dwarf with a third of the Sun's mass, plus a white dwarf, the corpse of a star that's died. This white dwarf is roughly Earth-sized, but it's 200,000 times more massive than our planet, so about 0.8 solar masses packed into a volume comparable to Earth. Now, the new data turned up additional pulsations with a much shorter period, just 2 minutes, showing up across multiple wavelengths, from radio to ultraviolet. And these 2-minute pulsations lead us to conclude that this white dwarf is a pulsar. But why do we call it a pulsar? Well, to be a pulsar, an object needs a powerful magnetic field, and to spin very quickly, a single white dwarf, left over from a star similar to the Sun, either alone or in a wide binary, will gradually cool and slow down its rotation. For an Earth-sized object to do a full rotation in just a couple of minutes, something must have spun it up, especially if the system's old. In this case, we do have that something, the close companion. In the past, the white dwarf probably stole matter from the red dwarf, speeding up its rotation. Today, there's no sign of mass transfer, but it could definitely have happened in the past, cranking up the white dwarf's spin and boosting its magnetic dynamo in the process. That made the magnetic field stronger, giving the white dwarf a shot at becoming a pulsar. Still, how do we know it's a pulsar right now? That's where the fresh observations and spectra step in. The star's emission includes a very unusual component: non-thermal radiation. Let me explain. Thermal radiation is electromagnetic radiation emitted by a substance with a temperature above absolute zero. That sounds like it'd be basically everything. But thermal radiation follows a characteristic spectrum, whereas non-thermal radiation, like laser or synchrotron emission, comes from particles cruising around at near light speeds. Observations of AR Scorpii did indeed reveal that kind of radiation, so there must be a mechanism accelerating particles to near-light speed. And what mechanism would that be? Yep, intense magnetic fields and jets. Additionally, part of the emission shows a specific type of polarization, another sign of strong magnetic fields. There are plenty more details and nuances here, but in broad strokes, astronomers piece together this scenario. The white dwarf is spinning rapidly, and its jets, as it rotates, blast right into the red dwarf. The jet particles rev up material in the red dwarf's atmosphere, so the entire system flares in brightness from our vantage point on Earth every couple of minutes. Unlike the more familiar neutron star pulsars, where we detect pulses directly from the beams as they sweep past us, in this system we basically detect the pulses as brightness boosts when the jets slam into the red dwarf. For that configuration to arise, a bunch of factors had to line up. A tight system, the white dwarf spin up, the right orientation, and so on. No wonder such objects or systems are incredibly rare. Since AR Scorpii was identified as a pulsar, we've found just one other similar setup in 2020. It's this system with a glamorous name, and it shares many properties with AR Scorpii. It also pulses at multiple wavelengths, from radio to X-ray. Finding a second one was hugely important because it confirms that AR Scorpii isn't unique, and that helps us better understand how such systems and white dwarf pulsars work. Yellow hypergiants are among the rarest stars. So rare, in fact, that in over 8 years of running the AI with Space Channel, I haven't mentioned them once. There are only about 20 known in our galaxy, and it's not because they're dim or something. It's quite the opposite. Setting aside certain gotchas, I'll explain shortly, these are some of the most luminous stars out there, hitting 500,000 or even millions of times the sun's brightness. Size-wise, they're also among the largest known stars, with diameters 1,000 times bigger than the sun's. But this situation is different from our previous white dwarf story, where that rarity was about needing a bunch of special conditions to form. Here, the reason has multiple layers. First off, the name itself hints at one factor: yellow hypergiants. At minimum, it's clear these stars are extremely massive. And like I mentioned earlier, the more massive the star, the rarer it is. But there's more to it. What exactly are hypergiants anyway? We've heard of giants, we know about supergiants, so hypergiants must be even bigger, right? In broad strokes, yeah, that's how it goes. But if you dig into the details, it can be trickier. The term hypergiant originally described stars of exceptionally high luminosity, i.e. brightness. Even though brightness generally correlates with mass, it's complicated because we're dealing not just with stars that are at midlife, but also those in late evolutionary stages. Supergiants, hypergiants, these are dying stars. Take a look at the Hertzsprung-Russell diagram, one of the most important tools in stellar evolution studies. Layouts differ slightly, but usually the vertical axis is absolute magnitude, i.e. a star's real luminosity, not how bright it looks from Earth. And the horizontal axis is spectral class or color, from blue hot to red, cool, or equivalently, temperature from hot to cold. You'll notice there's no direct mention of mass here, but if we look at the upper region, we see subgiants, then giants above them, then supergiants even higher, i.e. brighter. And at the very top we have hypergiants, initially labeled supergiants, which sounded pretty awkward. Later, additional nuances were added. For instance, some scientists proposed using the term hypergiant specifically for stars with certain spectral signatures that indicate extreme mass loss, while those lacking those signatures, but still just as luminous, might stay categorized as supergiants. So that's hypergiants in broad brushstrokes. Now, why specifically yellow? On the HR diagram, we also look at the horizontal axis for temperature. Yellow hypergiants mostly sit in the 5,000 to 7,000 Kelvin range at the surface. If you want Celsius, subtract 273-ish from the Kelvin temperature. But astronomers generally stick to Kelvin for stellar surfaces, so let's do that too. Crucially, no star is born a yellow hypergiant. That's a stage in a massive star's evolution. When we plot a star on that diagram, it's only capturing its current state, but over its lifetime, its temperature and brightness change, so the star moves around the diagram. All stars start life in roughly the same region, around the zero-age main sequence. Over time, brightness steadily climbs. For instance, our sun is about 30% brighter now than when it formed. But once a star uses up its core hydrogen and heads into its dying phases, its surface temperature changes dramatically. Those changes are shown by evolutionary tracks. Here's a detailed one for a star of 1 solar mass. But for higher mass stars and different chemical compositions, the track can be more complicated, especially for the most massive ones, which can bounce back and forth between the hot blue and cool red sides of the diagram in their final throes. The yellow hypergiant phase is a slice of that final thrashing around. The going theory is that stars of 20, 40, or even 60 solar masses might pass through it, typically after they've gone through a red supergiant phase. A likely reason we see so few yellow hypergiants is that it's an extremely brief stage, maybe just a few thousand years, which is a blink of an eye in the lifespan of even a massive star. Catching that brief moment is unbelievably lucky, and that's not all. On this particular phase, stars are shedding mass like crazy. Even before hitting yellow hypergiant status, they might have lost more than half of their original mass. Expanding into a giant lowers the star's surface gravity, so stellar winds can blow away huge amounts of material. At the yellow hypergiant stage, these ejections can form dusty shells around the star. Check out this photo of one known yellow hypergiant, IRC plus 10,420. You can see it's surrounded by an ejected shell of matter. Sometimes that material forms a pseudo-photosphere. Photosphere is the star's visible surface, while a pseudo-photosphere is a kind of fake surface in the dust. This can cloak the star's true temperature and brightness from us on Earth, so we might misidentify it. In other words, we could have observed more of these objects but not recognized them for what they are because their real surface is veiled by dust. That's yet another reason these stars can seem so scarce. They've also got other wild behavior. For example, a few years back, researchers pulled together new and archival data on certain yellow hypergiants spanning decades, letting them track how the stars changed over time. One star's surface temperature dropped thousands of degrees in just 2 years, from 8,800 Kelvin to 4,400 Kelvin. Imagine if our sun's surface got twice as cool in 2 years flat. Obviously, our sun is on the main sequence, and such drastic changes can happen. But still, another cool example of a yellow hypergiant is HR 5171, which turned out to be part of a contact binary. That means 2 stars are so close they literally share a common envelope, their surfaces touching. Either way, it won't last much longer before the whole system ends in a stellar catastrophe. In some cases, though, massive stars can move on to yet another interesting phase, the luminous blue variable, or LBV. Luminous blue variables are also extremely rare. Unlike the yellow hypergiants, though, I have mentioned LBVs once or twice on AI with Space. They share some similarities with the previous story. Again, luminous, blue, and variable all point to a massive star late in its life. LBVs can easily exceed 100 solar masses, though less massive stars can sometimes be classified there too. As with yellow hypergiants, they're rare partly because they're very massive, and partly because this phase is short, possibly just a few tens of thousands of years. The name basically hands you 3 traits. First, they're luminous. Near the top of the HR diagram, hundreds of thousands or even millions of times brighter than the sun. Second, they're blue, meaning they're extremely hot, anywhere from around 10,000 Kelvin to over 20,000 Kelvin at the surface. Third, they're variable, so their brightness changes with time. But there are plenty of bright, hot, variable stars out there that aren't classified as LBVs. What sets LBVs apart is their particular type of variability. Not only does the star's brightness shift, but its color also changes in sync, following a certain pattern called the S-Doradus cycle, named for the first star where it was observed. These cycles take several years to several decades. During that span, the star grows hotter or cooler, brighter or dimmer in a distinctive way. Here's an example of an LBV light curve spanning over a century. It tracks both brightness and temperature, showing how the star meanders through different spectral classes. This helps explain why they're so rare. If we need to see a multi-decade cycle to confirm that pattern, it's not enough to just catch a star in a single observation. We need long-term data, which we often don't have. So there might be more LBVs out there. We just haven't pinned them down. But that's still not the whole story. LBVs can also show sudden huge outbursts that make them look briefly like a supernova, even though the star ultimately survives. Some folks call these pseudo-supernovae, and I've done a whole episode on that. The most famous example is Eta Carinae. In the mid-19th century, it flared so intensely that it became the second brightest star in the sky, after Sirius. And that's despite being almost 900 times farther away than Sirius. Later, Eta Car dimmed so much it couldn't be seen with the naked eye at all. A handful of other LBVs have shown similar flares, collectively called Eta Carinae type stars. Watching them blow up like that requires even more luck and even longer observational windows, so that subset is rarer still. Eta Carinae, by the way, also left behind the Homunculus Nebula, an impressive structure we can see pretty well today. It's believed that after a star goes through the LBV stage, it often moves on to the next step, the Wolf-Rayet phase. At that point, the star might have shed all its outer hydrogen envelope, which can be nicely explained by the mass loss that happens during the LBV phase. But in recent years, evidence has turned up that some LBVs might skip the Wolf-Rayet phase altogether, going straight to supernova. So for some stars, LBVs are literally the final stage before the big collapse. You know which stars are truly the rarest? The ones we haven't found yet? Maybe you're thinking of exotic hypothetical stars, like dark matter stars. But I'm talking about objects that, by our current understanding, really should exist, though we haven't tracked them down yet. Either because it's unbelievably tough, like population 3 stars, the very first stars in the universe, or because they simply haven't formed yet and won't appear for tens or even hundreds of billions of years. Hello, black dwarfs, the cooled-off remains that today's white dwarfs might someday become. But like I said, it's wild how many different, mind-blowing objects and processes can show up in the universe just by squashing a clump of gas together. Subscribe to hit me with a like and comment, and I'll catch you in the next video.